Hello people, in today's lecture we learn the basics of solving differential equations. As you know, in mathematics, a differential equation relates one or more functions and their derivatives. Differential equations play a prominent role in many types of scientific theory and simulation. If you remember, in the past few weeks, we have seen several partial differential equations whilst avoiding any detailed discussion. This week, we discuss numerical approaches to solving a special class of equations known as ordinary differential equations or ODEs. The term ordinary is used in contrast with partial differential equations. In an ordinary differential equation, there is one independent variable, often referred to as t, and one or more dependent variable, which we refer to as y. If we consider t as time, the dependent variable y varies over time. The term dy over dt denotes the first order ODE expressing the derivative of y as a function f y, t. It is interesting to note that dy dt represents the change rate of y with respect to t. In today's lecture, we will discuss how to solve ordinary differential equations. In other words, we will obtain y as a function of t from its derivative function f y, t. In ODEs, we are usually given an initial value of y at some initial point t0 to obtain a unique solution for the unknown function yt. For example, we have a differential equation here in this slide. As learned in mathematics, we can analytically solve this equation by computing the integral of the function for t to obtain the result function yt. After computing the integral, we obtain the function y as shown here. In this formula, b is a constant. We should use the initial condition y0 equals 2 to find the exact value of b, which is 2 in this example. The differential function f depends on the two variables y and t. Let's consider a simple case when f is only a function of t. In this situation, we can analytically solve the differential equation and obtain function y. For example, suppose the differential function f is equal to ct, where c is a constant value. In this example, we can compute the integral of ft dt to analytically obtain function y as shown here. In this equation, b can be any constant. To obtain the exact value of b, we should use the initial condition along with the differential equation ft. In the previous slide, we considered the situation when f was just a function of t. Another simple case occurs if f is equal to fy. In this case, f only depends on the dependent variable y, not on t. Similar to the previous case, in this situation, we can also analytically solve the differential equation and obtain function y. For example, suppose the differential function f is equal to cy. By computing the integral of ft dt, the result function y is b e to the power of ct, as shown here. It is needless to say that b can be any constant. Like before, we can use the initial condition provided along with the differential function fy to obtain the exact value of b. While we can easily solve differential equations with one independent variable, for general f, it may not be possible to find any analytic solution, and we may have to turn to numerical methods. In today's lecture, we will discuss some methods of solving multidimensional and higher order differential equations using numerical techniques on computers. In mathematics, functions are usually expressed as continuous functions whose domains include an infinite number of points. So, the first step in numerical methods is to discretize the independent variable t. This way, we only have to consider a finite number of values. The simplest approach is to discretize the domain t with a fixed step size h. Therefore, as shown here, t is a set of discrete values. These values are labeled as t0, t1, t2, etc. After discretization of t, we need a numerical method to compute the integral of desirable differential equations. The most naive approach to obtain the solution function y is the Euler method, as formulated here. This series estimates function yn plus 1 based on the yn at a given time step n. It is needless to say that we have to use known initial conditions in the first step to obtaining y1. Then, based on the y1, we can obtain the value of function y for the next point in the domain. This slide illustrates how the Euler method works. Here, the blue curve represents a real function y which is unknown. However, we have its first order differential equation with a given initial value. The problem is to use the Euler method to estimate the function for some discrete points. While the blue curve yt is unknown, we have its starting point, which is denoted by a0. We use a0 and the differential equation to obtain a1 in the next step. After several steps, we estimate the unknown function y in terms of some discrete points, as shown by the red curve. The Euler method is simple, but quite inaccurate. The error between the two curves can be made small if the step size is small enough. However, the smaller the step size, the higher the computation cost. To increase the accuracy of the Euler method, we can use another approach named midpoint. In this method, for computing yn plus 1, rather than taking the value of function f at the point yn tn, it would be more accurate to somehow take the value of f at some midpoint between tn and tn plus 1. For instance, in this figure, it is assumed that yn equals the exact value ytn. The midpoint method takes the value of f at tn plus half h rather than tn. This way, the step size is halved and consequently the accuracy enhances. In the midpoint method, we don't exactly know the midpoint value of y, but we can approximate it by using the Euler method as shown here. So, the final formula for the midpoint method is formulated here. This approach requires twice as many evaluations of function f in each step. So, the midpoint approach has a higher computational cost than the Euler method. However, it can be shown that the error rate of each step in this approach is OH cube, whereas it was OH square for the Euler method. It means that the error of the midpoint method generally decreases faster as h getting closer to 0. In this figure, the red curve represents the real solution function y. As we can see here, the midpoint approximation highlighted in green is closer to the real solution than what estimated in the blue curve by the Euler method. In the midpoint algorithm, we halve the step size and obtain the value of function f at the intermediate point between tn and tn plus 1. To increase the approximation accuracy, it is possible to divide the interval between tn and tn plus 1 into multiple points, say into 4 intermediate evaluations. This method is generally known as Runge-Kutta. For instance, RK4 is one of the best known Runge-Kutta methods. To obtain ytn plus 1, the algorithm computes 4 Euler evaluations as formulated here. The final update is equal to the summation of the 4 intermediate solutions as presented in this equation. It can be proved that the error term is of order O h to the power of 5. All the examples discussed so far were for first-order differential equations. I mean, they only involve the first derivative dy dt. But we have important differential equations in practice involve higher order derivatives like d2y over dt squared. For instance, Newton's second law is formulated using a second-order differential equation as presented here. This law tells us how much an object will accelerate for a given net force. In this equation, x is the dependent variable representing position and F is the net force applied to an object. As you might know, m represents mass. In this equation, F is defined as a function of position, velocity, and time. You might know that d2x dt2 is the acceleration of the object and dx over d2 is a function determining its velocity. Now, to solve Newton's second law using the approaches already learned, a simple trick is to add one more dependent variable v as defined here, and then convert the second-order differential into a coupled system with two first-order differential equations. So, we define dx dt as velocity v, and accordingly, Newton's law is written as m dv dt equals f. In this problem, we added one further dependent variable y as a function of position x and velocity v. It should be noted that reducing higher order differential equations to systems of first order equations by introducing new variables is a general trick and can be used for differential equations with any order. In practice, we are not required to implement algorithms such as Euler and midpoint to solve ordinary differential equations. There are available libraries such as those in SciPy addressing the problem of solving ordinary differential equations. The only thing that we as user are required to provide are listed here. The user should provide a vector-valued user-defined function f. This function depends on a vector of dependent variables and a single independent variable. The second item that should be provided by the user is a vector of initial values y0 for the dependent variables. The last required item is an initial and final target value for the independent variable t. The library then returns the final approximation values of y and possibly a sequence of intermediate t and y values. Consider a simulation problem governed by the conservative form of Newton's second law. In this situation, an important feature of the system is that energy and any other desirable quantities must be conserved and remain unchanged during the simulation time. So, apart from finding an accurate solution for the differential equation, in conservative systems, the desirable quantities should be conserved during the simulation to have a stable simulated system. It should be mentioned that, unfortunately, the standard algorithm for ODEs don't do a very good job of conserving such quantities as energy. To address this problem, I will introduce another method named leapfrog. Leapfrog is an algorithm solving ordinary differential equations and works well for conservative systems. The algorithm is quite similar to the Euler method. It evaluates only positions on integer steps as the Euler method does. However, velocities are only defined for half integer steps. So the update rule for solving a second order equation like this is formulated as presented here. In these rules, x do computations with integer values, y v evaluates velocities on half integer steps. This slide visually illustrates how the leapfrog algorithm works. It is noteworthy that the error term in this algorithm is of order OH². To make leapfrog useful, there are two problems that have to be addressed. The first problem is about how we start the algorithm. We are usually given the values v0 and x0 at time t0 as initial conditions. But in the update rule, we require to have v1/2 to start the leapfrog method. The simplest approximation to address this problem is to do a single half step of Euler to obtain v1/2 as shown here. The second problem is how we can get the velocity v at the same time as the position x. To address this issue, the solution is to compute velocity based on two equal half steps, as formulated here. This method is known as velocity varlet. In this method, we first compute vn and half. The result is used to obtain the new position of the next step, which is xn plus 1. The new position is given to the new force function a to obtain the velocity at the time n. In lab 9, we first used the SciPy library for solving the ordinary differential equations. Then the leapfrog method is implemented in Python. Okay, that's all for today's lecture. Thanks for watching this video.